Okay, we learned about three decision trees in the previous lecture. And we learned about boosting, which was kind of meta algorithm, can be applied to any classification algorithm. So another thing that I would like to learn about is bagging. Bagging is basically, again, a meta algorithm, can be applied to any classifier that you have in order to reduce the variance of the classifier or the variance of the model that you have. So bagging stands for bootstrap aggregation. You know, bootstrap means that it's a pretty old puzzle. It means that you take your bootstrap and drag or up yourself up. Can we do that? Can we take our bootstrap and drag ourselves up? That was, an old puzzle. Usually, when we are doing machine learning or statistics, we have the assumption that our observation are samples from a distribution. So we observe some data points, and the assumption is that they're samples, they have been drawn, usually IID from a distribution. So if I can sample more points from this distribution, I can do many different things, all sort of inference about the model, the data. But in practice, usually we don't know this distribution. We can't sample from this distribution. The idea of bootstrapping or bootstrap samples is to assume that, okay, I have n data point. So I have n data points. Let's assume that the data points are a representative of this distribution that is unknown to me. I don't know the distribution, but I have n samples of that distribution. If you need to sample from this distribution, let's sample from this data instead. Okay? Because I don't know this distribution, let's sample from this data. If I sample from, I have a training set. If I sample from this data, it's called bootstrapping or bootstrap samples. Okay? So the idea of bagging is to take k bootstrap samples from the data and train k different classifiers or k different models, and then take average of those. It's very simple to do. So basically, the idea is to, first of all, bootstrap sample is uniform with replacement samples. You have n data point, k m point out of that. Uniformly, just randomly, uniform, give all points the same weight. With replacement, take one point and return it to the pool again and take another point. So it's uniform with replacement. So in bagging, take k bootstrap samples, train model HJ using the jth sample, and then take average of those. So I will take average of, say, j equal 1 to k of hjxi. And this is my estimation, my final estimation at point xi. And if this is classifier, so I will take the average. And if this is classifier, I have to compute the sign of this. Okay. So that's bagging. This reduces the variance of the final estimation, okay, by taking average of many models. And the models are trained using bootstrap samples, means uniformly you take different samples of your data set. For models with high variance like trees, it's quite useful. Don't forget that when this is the behavior of your training set. So the bias gets smaller and smaller when the complexity of the model is larger and larger. But the true error has a behavior of like this. So it means that, there's a variance. This is your variance, and this is your bias. Okay? So a very low bias model usually has a very high variance. Like tree, it's very flexible. You can fit your model perfectly, with training error 0. But it has very high variance. And you want to reduce this variance, you can do bagging. Okay? Okay, so how bagging reduce the variance? Suppose the error of each model is epsilon I, or we have high j, let's call it epsilon j. And also suppose that error or epsilon is drawn from So I assume that each of these models have this error, and I assume the errors have been drawn from a multivariate normal. Okay? So I make this assumption because, I just want to do some calculation to see what's going to be the final variance of this aggregation. So based on my assumption, the mean of this error is going to be 0 because I assume that it has been drawn from a multivariate normal. But expectation, the variance is going, let's assume that is nu, for example. Okay? And let's assume that covariance is C, Now, if I aggregate all of these, I have, what's going to happen? I have basically some variance and some covariance that I have to add. I have, I can write it this way. I have summation over I, summation over j, of this epsilon I, epsilon j's, divided by k squared, different possibilities. But this summation means that, either this epsilon I and epsilon j's are for the case that I is equal to j, or it's for the case that I is not equal to j. Means either we are considering the variance between, variance of a model, or we are considering the covariance of two models. Okay? So, and there is 1 over k squared here. So how many of these terms are there when I have k models? K, right? So I have 1 over k squared. This is k times this is the case that I is equal to j. So basically it's epsilon I times epsilon I. So it's variance, right? So it's k nu, because the variance was nu. How many of these terms are there? K times k minus 1. Because considering each model with another model, if they're not the same model. So there is k times k minus 1 covariance, which is C. Okay? So this is going to be nu over k plus it's nu over k plus k times k minus 1 over k times C. Or, sorry, just k minus 1. So I just cancel this k with this one of these k. So it's 1 over k nu plus k minus 1 over k times C. Okay? Now consider two cases. Consider a case that all of these models making the same mistake. Means they are correlated. Means the second model acts as the same as the first model. The third model acts the same as the second model. So in this case, this C, the covariance between two models, is basically the variance, right? Like epsilon I is the same as epsilon j, because there's correlation between these two models. So if epsilon I is if models are correlated, if in the worst case, if epsilon I is the same as epsilon j, then this C is going to be nu. And this is going to be 1 over k nu plus k minus 1 over k nu, which is going to be nu plus k nu minus nu over k. It's nu. The original variance of the model was nu. Nothing changed. So if I aggregate k models, when these k models do the same thing, or correlate, make the same mistake. So I haven't gained anything. But if they're uncorrelated, if models are uncorrelated, if they're uncorrelated, what is C? Sorry? C is 0. The covariance is 0. So in this case, C goes to 0. And the total variance would be 1 over k nu. So the original variance was nu. Now it's 1 over k nu. If I aggregate k models that are uncorrelated, I reduced the variance k times by this just aggregation. So basically, bagging can help and reduce the variance significantly if you choose the models to be uncorrelated. Okay? So in terms of tree, you can do bagging for tree, but you can do something way better than just simple bagging. It's called random forest. So random forest is some sort of bagging, a variation of bagging. But it works pretty well in practice. So I say variation of bagging because if you just apply bagging to trees, to decision trees, unfortunately, most of these or all of these models are going to be correlated. And nothing actually is going to happen. Basically, if you apply tree on a subset of your data, that's what bootstrapping means, right? Imagine that you have a subset of your data, a subset of your training, or a bootstrap sample of your training, not all of the training points, and you fit a tree on it, and then you take another sample, fit another tree on it. So these models are going to be pretty correlated. They act almost the same, you know. And then when you do bagging, it's not going to help because it's not going to reduce the variance. So random forest is a very interesting idea and a very simple idea. That instead of fitting a tree on a subset of data points, fit it on a subset of data points and a subset of variables. So that's my data. It's D by N. Bagging roughly means that I take a subset of these columns, some of the data points, and fit a tree on it. Random forest means that not only take a subset of these columns, take a subset of rows. Don't use all of your variables. You have 100 different measurements for each data point. Use 50 of them instead of 100. Use half of them. As if 50 of these measurements haven't been observed at all. We never had them. Okay? So you have a data point, and it's like blood pressure, cholesterol, and weight, and the fact that this person is a smoker or is not a smoker, and you want to fit a tree, you know, the examples that we had on the other section. You want to fit a tree to see the chance of, you know, heart attack. Don't use all of these measurements. Randomly choose some of them, just cholesterol and weight this time. Next time, just cholesterol and you know, blood pressure. Next time, just blood pressure and weight. You know, a subset of these inputs and subset of variables and subset of data points. So feed a tree each time on those, and then take the average. So it's called random forest. And random forest has a very good performance in classification. Okay? Any question? Okay. So I promised to give a short lecture about convolutional neural network, and I'm going to start convolutional neural network. I'm not sure if we can finish that today, but So we have learned about feed-forward neural network in this class. Convolutional neural network is most of the success stories that you have heard about deep network is about convolutional neural network. So convolutional neural network by itself is pretty old idea. It's not new, but it has been used recently extensively in image processing, in natural language processing, and it shows very good performance. In classification, they have state-of-the-art, you know, record for many data sets in classification and pattern recognition. So convolutional networks are simply neural networks that have one layer of convolution. So in feed-forward neural network, neural networks, if you recall, you know, we had a layer which was input layer, and then we had some output layer, and we had some hidden layers, right? So between input layer and hidden layer, or between a hidden layer or another hidden layer, we had a set of weights. So you can basically think that this layer is mapped to this layer through a matrix multiplication. So if I have like n point here and m nodes here, all of these weights can be captured in a matrix of n by m matrix. And you can imagine that this input has multiplied to this linear transformation, have been mapped here, like in the in pre-activation stage. And then an activation function, like a sigmoid function, will be applied to it afterward. But before, pre-activation, it's just matrix multiplication, right? Now, this is feed-forward neural network, and it happens to the next layer and so on. In convolutional neural network, at least, there is one layer that instead of the simple matrix multiplication, we have a convolutional layer. One of these layers is what we call convolutional layer, which I'm going to explain what this convolutional layer is. It is sort of matrix multiplication, but it's a sparse matrix multiplication, as if some of these weights are 0, and there is some constraint on other weights that under some conditions, some of these weights are going to be equal. Some of the weights should be shared, and some of the weights are 0. So this type of layers are called convolutional layers. Each convolutional layer has 3 stages. So one of them is convolutional stage, the other one is detector stage, and the third one is pooling stage, which I'm going to explain each of them separately. So let's start with convolutional stage. These 3 together make one convolutional layer. Okay, let's start from convolutional stage. So convolutional stage, you are familiar with convolutional operator in mathematics, right? You can convolve x with v, for example, with w. At point t, the convolution of x and w is this integral, x of a times w t minus a, over the whole space. And we usually use this notation to show the convolution at point t. You can define convolution for discrete functions as for discrete signals as well. For discrete signals that are defined only on, say, for example, integers t or a, then you have summation between negative infinity and plus infinity of signal a, signal x, and signal w. When there is a lag, you just t is 0, for example. When t is 0, you go from negative infinity plus infinity, you shift the signal and multiply it to the other signal and then add them up. Okay, let me show you this. Before I show you this in MATLAB, if instead of wt minus a, if I have wa minus t, it's not called convolution. It's called what? Do you know? Sorry? It's called cross correlation. The difference is that when you have w like a minus t, it's the signal that you're shifting. When it's t minus a, because of this minus a, as if you're flipping the signal, and then you shift it, right? In convolutional neural network, most of the time, we are using cross correlation. But it's called convolution, in the literature they call it convolution. Technically, usually it's cross correlation, not convolution. See, I have 2 signals, say that's signal x and that's signal w, discrete. I want to compute cross correlation. It's not convolution. So cross correlation means that set t to some values. Say, for example, t is 0. At point 0, I want to compute the convolution of the cross correlation of these 2. So basically, I have to multiply this number by this number, plus multiply this number by this number by this number, and so on. So I make this multiplications, add them up. That's convolution at time t equal to 0, okay? Or that cross correlation. So interchangeably, I'm going to use cross correlation or convolution. So basically, convolution is when you flip the signal, okay? or kernel. So that's at time t equal to 0. It's 7.6. Then I can set t equal to 1, means I shift this signal one step, and then I compute the same thing. But this time, these numbers are going to be multiplied. And this summation was from negative infinity to plus infinity. We just assumed that outside of this domain, the value of the signal is 0, so there's no value. You just need to compute a finite summation instead of infinite. So this is the cross correlation, and that's at time 0, at time 1, and that's at time 2. So now at time 2, 3, 4, and you can do it for negative values as well, just negative t equal negative 1 and so on. Okay, then I have this sequence. If I look at this sequence from negative 6 to plus 6, these are the value of cross correlation. Some of these values are large. This is 17.42, or the largest one is 19.41. So what does it mean? At time 2, it's maximum. And the second maximum here is at time negative 1. Sorry? There's a huge correlation here. Okay? There is a huge correlation here, and the second maximum one is here. At time 2, at time negative 1. Let's look at time 2 and time negative 1 again. So time 2 was large. See? At time 2, there is a big similarity between these two, right? So we get a large number. And then it could be a small. In negative 1, again, it's large. See, here, this is very similar from this. So at negative 1, again, there's a similarity between these two signals, right? So basically, I can, using this cross correlation, I can find the correlation between these signals, and I can compute the similarity between them. And, you can define convolution or correlation for multidimensional signals. It doesn't need to be one-dimensional signal, as I showed you. It could be like two-dimensional, could be three-dimensional, and it's quite common to use it in two-dimensional in convolutional neural network, because your input could be an image. You applied an image, you convolve an image with another signal. And in the literature of convolutional network, this another signal usually is called a kernel. So we convolve an image with a kernel. Okay? So convolving an image with a kernel means finding correlation between them if you compute correlation. This is the difference. This is cross correlation, this is convolution. The only difference is that in one of them you flip the signal, in the other one you don't. Okay, see, I have an image here. Let me show you this tree line. So, I have this image I. This is my image, okay? And I have this K. I have this K. This is K. It's a 3 by 3 matrix. Image was way larger than this, my image I. This is just 3 by 3. And it is one, if you look at this, it's 1, 0, negative 1. Okay? That's K. 1, 0, negative 1. And that's the form. So, knowing that this example, one-dimensional example that we did, when you compute the cross correlation between this signal and another signal, you find in each time t, you find the similarity between them. You capture that. What's going to happen if I convolve this small k image, this small kernel, with my original image? What's going to happen? The original image was elephant, right? This kernel is 1, negative 1, 0. Means if you look at these 3 lines, there's a contrast here, I have like white and black, and between them I have gray scale. Yes?
Were you asking what would happen?
Yes.
When it detect any place in your original image where you have like a gradient like that? Mm-hmm. Like that'll show high convolved or cross correlation, and then another way you have to smooth the opposite.
Exactly. I mean, we are going to capture the patterns similar to this in the original image, And patterns similar to this means the patterns, the pixels that we have contrast. We go from blue, if we go from, there's no blue here. We go from like white to black. Where in an image you go from white to black? Sorry? Edges. Edges of a picture is where you have high contrast, right? You change the color rapidly. That's what edge is. Okay, that's this is when I convolve a kernel with this image. That's the result. And that's when I convolve the transpose of this kernel with this image, and that's the result. And this is basically summation of these two. But look at these two. Can you see edges of the original image here? And is it visible that here, the edges, like the vertical edges have been captured, and here the horizontal edges have been captured? I can show you a better example. Okay, see that's my original image. When I convolve it with this one, I capture only horizontal edges. And when I convolve it with the transpose of this, I will capture, the vertical edges. Okay? Any question here? Okay, so it's clear that if I have a good kernel, I can convolve it with my image. For example, suppose that we are doing image processing. If I have a good kernel, I can convolve it with my image and capture some useful features, Say my task is to recognize if this is an elephant or if it's not an elephant. When I look at the original image, there are many details in it. I don't need these details. I just need to know the final shape. So it's a useful feature if we want to do elephant detection. Okay? So, so that could be useful to capture images. In convolutional neural network, we are going to convolve, in each convolutional layer, as I told you, there are 3 stages. The first stage is convolution. We are going to convolve a kernel with the image. But the kernel is not a fixed kernel. It's a kernel that we are going to learn. Okay? So this is basically what's going to happen. So suppose that this is my original image, and this value that is in red is the value of my kernel. Okay? But in convolutional neural network, we have to learn these values through the training process. But for the moment, assume that they have been learned already and we know the values. And it's 1, 0, 1, 0, 1, 0, and so on. So when we do convolution, means that I make multiplication of the value of this kernel with the value of the images, and I sum them up. It's going to be 4. 1, this is 0, 1, 2, 3, 4. 1, 2, 3, 4. So it's 4. Okay? Then I shift my signal and do the same thing. And then I shift my kernel, do the same thing. And just I go pixel by pixel, horizontally and vertically, and compute, This is called convolved features. That's the first stage of a convolutional neural network. Okay, if you think about this, it is as if, here in feed-forward neural network, we had a dense W, which was weight between this layer and this layer, right? But here, actually, it's as if, a kernel has been applied to this tree, for example, and we took the summation, and this is the summation. Then I applied the same kernel to this tree. And I computed the summation, and that's the summation. And then I applied this tree, and so on. 2 things is going to happen. First, I impose some sparsity here. It's not dense. In the past, I had, a link between these 2. I don't have it anymore. I had a link between these 2. I don't have it anymore. So first of all, it's not a dense set of weights. It's a sparse, as if this link is 0. That's the first restriction or the first constraint that we are imposing here. And the second one is basically the fact that, these weights are the same. In the feed-forward neural network, all of these weights could be unique, could be different from the other one. But here, these are values of the kernel. The same kernel is going to be applied now to this tree. So basically, this is the same as this one. This one is the same as this one. And this one is the same as this one. Okay? So there are 2 important constraints. One of them is sparsity. And the other one is that these weights are equal. Okay? So it's going to make our model way less flexible because of this sparsity and this weight sharing compared to a simple feed-forward network. In next lecture, I'm going to complete this and show you basically other stages of this network and how we can put them together. And also, hopefully, we're going to have time on Thursday to do a little bit of theory of like pack learning to be, at least get familiar with this concept in classification. And next week, we start presentations. Oh, by the way, another important thing. Those who need to have access to SharkNet. Yeah, I think I told you that we are going to make some general user and then assign it to you. Due to some technical difficulty, it didn't happen. We can't do that. So if you applied for an account, you can use it. That's valid. If you haven't applied and you plan to apply right away. And on Piazza, I put the link to the procedure, what's the steps to do that. Apply right away because either on Thursday or next Tuesday, someone from SharkNet is going to give a very short, like 20 minutes tutorial how to use this machine. And it's very useful if you have the account and you can do basically the steps that SharkNet tutorial is going to explain. Okay?